Hello and welcome to the last session of our OptiSPICE software package. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be assisting your host, Jem Bonfill. The webinar today will focus on advanced applications of OptiSPICE. As with previous sessions, we will have 3 polls that we will launch. Please take the time to vote on them. We'll also have 2 question and answer periods at the halfway mark of the presentation and at the end. And lastly, we're going to be recording the webinar and emailing the link to everybody. The email will come in tomorrow at noon Eastern Standard Time. With that said, let's get the webinar underway. I'd like to introduce your host, our product manager of Optoelectronics, Jem Bonfill.
Hey, Brian. Thanks for the introduction. Today I'm going to be talking about OptiSPICE and its advanced applications. But first, let me briefly give you a small overview of OptiSPICE for the ones who have missed our previous presentations. So OptiSPICE is based on well-known Berkeley SPICE, which is a standard tool in the industry for simulating electrical circuits. The way it works is it takes basic components such as resistors, capacitors, inductors, and which have their own simple compact models, or it can take nonlinear, more complicated components like BJTs, MOSFETs. It takes all the equations that describe these components and then how they're related to each other and places them on a large matrix. And then solves this large matrix one time step at a time. If you're doing a transient analysis, if you're doing a frequency domain analysis, then it would give you a solution at a particular frequency at a time. Now, on top of this basic infrastructure, we have built optical capabilities. In contrast to electrical signals like voltage and current, our optical signal is a complex number. This is because we have to simulate the carrier, which has a magnitude and a phase. But if we want to simulate the carrier in full, we would have to go and take very small time steps because a laser signal, a signal generated by a laser will have a frequency in terahertz range, where we're looking into electrical bandwidth, which is going to be in gigahertz range. So the way we're avoiding this problem is actually just simulating the envelope of the carrier and the phase. So by keeping the phase in the envelope, we can still do interference effects, for example. And every optical signal has its own mode, its own channel, and they're bidirectional, and it is associated with a phase. Every optical component in OptiSPICE can handle multi-mode, multi-channel interactions, and then it is also bidirectional. So we have, on top of basic electrical components like resistors, capacitors, inductors, and nonlinear electrical components like transistors and MOSFETs, we have splitters, optical splitters, joiners as linear optical components, and we have a laser, waveguides, and photodiodes for modeling the nonlinear part of the optical circuit. With that said, I am going to briefly talk about the strengths of OptiSPICE and its applications. Why would you want to use OptiSPICE? One of the main features of OptiSPICE is, of course, simulating an optical link in a telecommunications circuit. Unlike most regular simulators, OptiSPICE can handle both the electrical part of your design and the optical part of your design at the same time. So what this means is you can have your laser driver circuit with your transistors, resistors, and capacitors, and then you can use that to drive a laser, which then will generate an optical signal that can be carried through an optical fiber. It can be amplified if necessary, and on the other side you can have a detector photodiode and then a transimpedance amplifier simulating a standard optical link, electro-optic link. One of the other strengths of OptiSPICE is being able to create control circuits. For example, let's say you have a laser and a laser driver in your design, and that is generating heat. Near this laser, we have an optical component, a ring resonator, which is very sensitive to temperature changes because the temperature will affect its resonance. Now we can have a third piece in this puzzle, which is the controller. The controller will control the resonance of the resonant frequency of the ring resonator by heating or cooling it down. So as your laser heats up, it will affect your ring resonator, and then your controller will react. So this kind of system you can actually easily simulate in OptiSPICE. So as you might have guessed, I started talking about the thermal effects. So OptiSPICE can actually handle multi-domain simulations at the same time. Thermal being simulated as an RC circuit. We can do optical and electrical. OptiSPICE can also simulate full photonic integrated circuits. As they have only a few hundred components, it is well within reach of OptiSPICE, where you can simulate your entire optical circuit, including the electronics around it. And we're working towards getting a design flow where you will be able to import models and devices that are built by foundries and do your design, and then look at the layout and go between your layout and your design, such that you can optimize your simulation and you can optimize your design using your simulation. Now let's look at the advanced applications for today. We have 3 of them. The first one is the traveling wave modulator, which leverages the advantages of SPICE, as we can do both electrical and optical simulations. The second one is a ring resonator gyroscope. It uses Sagnac effect, which we will discuss in detail, but it's a very sensitive gyroscope, and we can simulate this on OptiSPICE. Finally, we're going to be looking at a telecommunication example, where we're going to be doing a phase lock loop, optical phase lock loop for homodyne detection of a BPSK, binary phase shift keying signal. Okay, so the basis of a traveling wave modulator is actually a standard Mach-Zehnder modulator. So I'm just going to briefly describe how a Mach-Zehnder modulator can be built in OptiSPICE. The basic components are a splitter, a joiner, and then 2 waveguides. Now these 2 waveguides can be controlled, so the refractive index of these waveguides can be controlled using a voltage source, and it can be changed. So as you change the refractive index of both or a single arm, you will see that the output of this Mach-Zehnder modulator is going to, at the output of this Mach-Zehnder modulator, the waves coming from different arms are going to either interfere constructively or destructively, therefore you can modulate your signal. Now the way we control this multi-layer filter, you can actually establish a relationship between the voltage applied and the change in the refractive index. You can establish a polynomial relationship. It can be a first order or second order polynomial. And we can also model carrier injection and depletion effects the same way. So this basic design is usually, they're more compact compared to the traveling wave modulators, but usually they can't go as fast as the traveling wave modulator design. You can set this multi-layer filter using 1 or multiple layers if, let's say, your contacts that you're applying the electric field from are not covering the entire waveguide. This is also possible. Now let's look at how we modified the traveling wave model in order to get to a traveling wave modulator. So we have initially we didn't have any metal contacts, or they were just basically a voltage connection into the multi-layer filter. Now the way we have improved this model is actually by adding the transmission line, 2 transmission lines to model the metal contacts. What happens with a traveling wave modulator is actually it is a lot longer than a regular Mach-Zehnder modulator. Therefore, the metal contacts actually work as transmission lines. This allows you to actually use a smaller voltage to induce a phase shift, since it is going to accumulate over the length of the waveguide. Again, the phase shift is achieved by changing the refractive index of the multilayer filter. And this multilayer filter is actually divided into many little sections. And each section, and the transmission line is also divided in many little sections, and we're going to look into the details of the transmission line in the next slide. And each layer of the transmission line corresponds to a layer of the multilayer filter. And the electric field that is generated in the that is applied to the metal contact controls the refractive index in the multilayer filter, and as the signal travels through the transmission line, the refractive index in the multilayer filter also changes in time. So now let's look at how the transmission line looks on the inside and how we have modified the standard transmission line model in order to model the PN junction effects, which is the carrier injection or carrier depletion. The standard transmission line model, as I said in the previous slide, it cuts the metal contact in multiple sections, and each section is modeled as an inductor, resistor, capacitor, and a conductance. And these values are actually, these parameters are entered as per unit length and then distributed over the entire device. Now, one modification we had to do in our transmission line is to add actually a resistor in parallel with a capacitor or a diode, depending on the bias of the diode, in order to model the PN junction across the transmission line, which is in silicon. It is used to inject carriers, which in turn changes the refractive index. Now, finally, we have there are two ways of creating subcircuits in the transmission line. In OptiSPICE. One way is actually building in the circuit, as you see here. The other way is actually writing a netlist, a subcircuit netlist, and this is what's being done over here. And this model ships with our software. One of the effects that is very important to be able to capture in the traveling wave modulator is the velocity mismatch. What happens when, in the transmission line, which models the electrode of the traveling wave model, the signal travels at a certain speed, and then in the waveguide, signal travels, we have our optical signal traveling at another speed. If these speeds are the same, we have, this is the best way of achieving maximum Q factor and maximum modulation efficiency. But when they're different, what's going to happen is the optical signal is not going to accumulate enough phase shift. Therefore, it's not going to, we're not going to be able to modulate the signal as well. And you can see the difference in this eye diagram. Now let's start talking about our second example. Now, this example is ring resonator gyroscope. It has many different sections, and I'm going to go through, as we talk about this example, I'm going to go through what each section does one by one, and then I will talk about how the overall design works. Now, let's start with the first part, phase modulator. What it does is actually it creates a phase shift in the optical signal, and this phase shift in the optical signal, depending on how the rate of change, it will shift the frequency. Let's say if you have a linear increase in phase, this will translate to a shift in frequency. Depend on if it's an increase or decrease, linear increase or decrease, then you will get an increase of frequency or decrease of frequency. Then we have our ring resonator here. That is the most important part of this gyroscope. What happens is this one gyroscope is actually built only for one axis. When you have rotation, what happens, and a signal traveling around this ring resonator, clockwise or counterclockwise, with the rotation, due to sine effect, the signal traveling around the ring resonator sees either a longer or a shorter path length, which in turn means that the resonant frequency, the effective resonant frequency of the resonator shifts. By capturing this shift, we can actually we can calculate the rotation speed. And the resonant detection circuit here actually makes sure that we are capturing whether the ring resonator is on or off resonance. And actually, in this example, it's we make sure that we keep the ring resonator at on resonance at all times, so that we can calculate the difference in the change in resonance and use that calculation to calculate the speed. So the circuit gets signals from different parts and then uses this photodiode to figure out if the ring is on resonance or not. If the ring is not on resonance, then it generates an error signal, which then is sent to a controller, which then generates the control signal for this optical phase delay. And then finally, at the end, we can calculate using the change in the frequencies. Then we can calculate the speed of rotation. Now we're going to take a quick break and do a second poll, and then I'm going to take a few questions, and then we will continue with the presentation.
Okay, thanks, Jim. The second poll is up for all you guys to answer, and this is going to be the final OptiSPICE session for our webinar week here. So now that you have your last chance to ask Jim anything you'd like, please take the opportunity. Of course, we can answer things offline as well. You can contact Jim directly or email support or ask questions on our forums. And the way that the forums work basically is you can ask it to the community. We do have all our staff looking through the questions posted on a daily basis. So we try to answer as many as we can in the forums, but right now it's generally the best opportunity to have a one-on-one with Jim and ask him any SPICE questions that you guys may have. I'm going to give it a couple more seconds. I'll close the poll, and I'll let Jim take it over now.
Okay, we have one question here asking if we're going to be distributing our presentations. Yes, once all the webinars are complete, we will put them on our website. And actually, these specific examples that are are already on our website. You can go and download. You can go under OptiWave and find the section that has the information about OptiSPICE, and we have the slide deck over there. I'll wait a couple of more seconds if, in case there are any other questions. Okay, so let's move forward with the presentation. Now here we have a basic result from a ring resonator simulation. It's just showing the analytic calculation for the transmission for the output of the drop port and output of the through port. This is actually the drop port. You can see the resonant peaks which can be calculated by using the radius of the ring, and it needs to be a multiple integer of the wavelength. We can also calculate the expected analytically calculate the expected free spectral range or full width half max, and the analytic solution we get matches completely. The simulation result we get matches completely the analytic solution. So the way the phase modulator works is I have a simulation result for a basic phase modulator here. Is we apply a linear phase shift like I described earlier, and the rate of this phase shift, the rate of change over time, will actually induce different frequency shifts. And you can see the simulation results over here, where at time 0, as starting from time 0, as we're changing the phase, the ring goes from the signal goes from on resonance to off resonance, and based on the rate of change here, we see that the signals go a different distance away from the resonance. Now, a second part of this, another important part of this simulation, again, is how we set up the ring resonator to simulate the Sagnac effect. We have for simulation of the Sagnac effect, we have a counterwise and counterclockwise moving signals, and they get into the ring resonator from two different ports. One of them goes counterclockwise, the other goes clockwise, and I have split the signals into two here because we need to control the length of the multilayer filter, or one section of the length, using a voltage controlled source, which will in fact simulate the change in the resonant frequency. And we would like to, for the signal going one way, the change in length is going to be positive, and in the signal going the other way, the change in length is going to be negative. Then by capturing the difference in frequency in two different signals, then we can actually calculate the rotational speed by using the formula where n is the refractive index, L is the length or the total radius, lambda is the wavelength, divided by the number of turns. In our case, it's only one turn, but you can make this ring resonator much larger, or you can wind it multiple times. And A is the area of the ring resonator. Now, the way we keep this carrier, keep track of the resonance, is using the balance detectors. We need to generate an error signal signaling the controller that the ring is going off resonance, and then the controller needs to generate a signal to correct the frequency, the input frequency, such that it is always at resonance. As you can see here, we have two signals combining in this cross coupler. One is from the drop port, the other is actually from the incoming signal. The stop result is from the drop port. You can see as the length and the x-axis is the length. As the length is either increasing or decreasing, we're going off resonance at a constant frequency. And the output of the cross coupler combined in the photodiode is giving us our error signal. Now, if we start in the middle where there's no difference in length, then our error signal is 0. Then you can see that our error signal is increasing as the length is changing, as the effective length is changing due to the Sagnac effect. You can see that if the rate of change is too fast or the rate of rotation is too fast, then we're going to be going into this region where our error signal is not going to be correct. It's going to be decreasing with length, which is not correct. So we have to make sure that our error signal stays within this region at all times. The circuit we have used for the controller, it's called a PID controller. It is very common for control systems, and it uses an error signal and a series of operations. PID is coming from a proportional, integral, and differential. In this case, you don't have to use all of them at once. We're using the proportional, a signal proportional to the error signal and the integral of the error signal, and then adding them together. We have an RC filter at the end to make sure that our output is smooth. And we don't want the controller to swing things too fast that might make the simulation and the circuit unstable. And finally, we have our integrator here, because using the controller, I'm actually changing the frequency. A constant change in frequency is equal to actually a linear increase in phase. So because we're modulating the phase, I'm actually integrating the output as it's the change in frequency. Finally, we have the results here. This is the output of the drop port into in the ring resonator. You can see initially we start with a certain rotation, so the drop port is not completely at the ring is not completely at resonance, and slowly the controller actually is changing the frequency output of the laser such that both the clockwise and counterclockwise signals are at resonance. This is the balance detector. This is our error signal. So our error signal is pretty large at the beginning, and it trends to 0 as we're getting to resonance. Here we're looking at the frequency difference between the two arms, and it's about 75 kilohertz. And we can use this to calculate the speed, and you can see the way we detect the speed is initially we're not detecting anything because we have a huge error. However, slowly as the error is getting smaller and smaller, we're calculating the correct value. And in fact, I started with a very close value to what we got at the end. And I'm going to show you actually how the simulation runs. One moment, please. I need to get my connection back.
While Jem's doing that, please note that the final question and answer period is coming up. So if you have any questions, please write them down now. And definitely thank everybody for joining us on all these sessions. We have 2 more in the afternoon, so I see a lot of familiar names coming to most of these, so thanks to all you guys for that. Just give Jem a second here to get his remote desktop set up again. And if you guys have any, again, quotation requests, or you would like to get an evaluation set up, you can email us at info@optiwave.com. And everything else that you might have questions about, just send it straight to support@optiwave.com, and that goes out to the entire team here. So pretty much all the product leads of all our different software tools, they'll get the email. Sales team will get the email as well, and the appropriate person will get back to you on whatever your question is about. Okay, I'll pass it back to Jem. I think he's set up now.
Okay. Yeah, thanks, Brian, for filling in. We had a disconnect Okay, let's run this simulation. First, I'm running the simulation with the controller on, and I'm going to show you what happens when we turn the controller off. Let's look at our rotation. You can see we're getting about 3.5. The error signal is, they're both decreasing. Now let's go back and disconnect our controller. There are two connections here that are not apparent. The first one is over here. This is the way we're controlling the change in length or the rotation. And here we're actually controlling this, the output. Now let's disable the change in the phase. So our controller is disabled. Now once we run the simulation, we're going to see that the error is going to keep on increasing. It's actually not going to decrease at all. I'm sorry. The error is not changing because we're not controlling the phase. Therefore, it stays the same. And the power at the cross couplers, they're also not changing. So let's go and look at our final example now. Our final example is about optical phase lock loop for homodyne detection. On the left side, we start with an input signal. It's a BP binary phase shift keying signal, so the phase is either 0 or pi. And this simulates the transmitter. And then on the receiver side, now we have a local oscillator, which is a laser, and we have a 90-degree hybrid, balanced photodetectors, which then calculate the real and imaginary part of this BPSK signal. We have a circuit that calculates the phase difference between the local oscillator and the input signal, the carrier frequency. And then finally we have a controller. Again, it's a PID controller with only integral and proportional term that controls the frequency of this laser. Initially, you could see, I'm going to go through every part one by one. Initially, you could see we have two signals coming in with a certain frequency and certain phase. And at the 90-degree hybrid, they're mixed together. So at every output, we have a combination of the two signals and a phase shift applied by the 90-degree hybrid. The first arm has 0, then pi, 3 pi over 2, and pi and a half. And then in the balanced photodiode, we're actually, each photodiode calculates the power incident onto the photodiode by calculating the optical signal and multiplying its complex conjugate and dividing by 2. So here you could, we're starting with these optical signals, O1, O2, O3, O4, and then we're multiplying it by itself, by its complex conjugate, and this is the result you get. You get a constant shift and then a varying signal based on the difference in phase or difference in frequency. And every output has a different phase relative to each other. Now, once these signals are combined in the balanced photodiodes, now we're subtracting them from each other, then you only end up with these sine and cosine terms, and then you also have a term describing how the sine and cosine changes over time. It's given by this equation, where omega 1 and omega 2 are the frequencies of the local oscillator and the phase offsets of the local oscillator and the input signal. Now what happens at the detector is, you can see when we subtracted the two equations together, we end up with an A times B times cosine term and then a sine term. However, if the frequencies are the same and there's no phase difference, then the output in each arm is proportional to the real and imaginary parts of the incoming signal. And one thing to note is our photodiode completely filters out the higher frequency part of this term, so we only get the low frequency part. And as you can see from the simulation result, the signal is actually only going between 0 and pi, or 1 and -1 in the real axis, and the imaginary axis is it's completely 0. Now what happens when we have a difference in frequencies, then you end up getting your signals start to rotate in the constellation. So your I and Q signals, they start to rotate. And we can easily see that by looking at the sine and the cosine terms here, which are non-zero and they change over time here. This is a result where the local oscillator frequency is different than the frequency of the incoming signal, and you can see that the rotation in the constellation over here and the rotation in the phase of the signals. Now I don't get a full 0 on the imaginary axis. Now the way we calculate the results, the error signal is actually by simply multiplying the I and the Q signals. What this gives us is a term sine 2 theta, which then can be approximated as equal to theta. Theta is our difference in phase. Therefore, as long as the phase difference between the two signals are small, we can use it as an error signal. Well, normally in electrical circuits, calculating the multiplication of two electrical signals are not straightforward. You usually do that with amplifiers or transistors. But just to keep things simple, we have implemented a simple multiplier element which does this, which performs this operation mathematically. So we get the I and the Q signals and then multiply them together, and we can get the result of the error signal directly. Finally, we have our loop filter, or PID controller. Again, similar to the example before, we have an RC circuit which makes sure that there are no sudden changes. And we have proportional and an integral term. And this gets the error signal and then generates the control signal for the laser. Now, here's again the example of the output. As the phase lock loop is off, we're seeing the change in the constellation visualizer, the rotation in the constellation visualizer, where if they're equal, we're supposed to get one signal over here and then another signal over here, which is the real and imaginary axis over here. And finally, when we turn on the phase lock loop on, then it ensures that the local oscillator has the same frequency as the carrier signal. Therefore, we can recover our signal cleanly. That ends my presentation. We're just going to have a quick break and have another poll. And then after the break, I will answer some more questions.
Okay, final poll for this session. Same poll that you guys have seen if you've been to previous sessions. we're just trying to gauge basically the attendance for each session. So again, if you have answered in the past, please answer it again. We're just going to use this information to put together future webinars that are more applicable to the specific interests of the people attending them. And of course, all these webinars are going to be made available afterwards anyhow, so you can take a look at that and go through everything. And down the road, we're going to try to streamline the video, the actual video material, probably go over the audio again. So we're going to try to cut each of these webinars down to maybe a nice concrete 20-minute video, post that on our YouTube channel, and hopefully it is nice, neat, and tidy, gets to the point quickly for anybody taking a look at it. So I'm going to go ahead and close the poll now. We do have, I think, one question posted, so I'll pass it back to Jen.
Thanks, Brian. We'll answer this question directly with the user. So I'm just going to wait for if there are any other questions. Okay. Well, thank you very much, everybody. Thanks for listening to this webinar. I hope you enjoyed it. Have a good day.